Okay. Welcome everybody to the next edition of the FIX seminar. Today Vergence is speaking. He is a relatively new member of Jochen's group, I think. And
10 months.
Yeah, okay. So okay, not really. Absolutely new. And he did his studies in India and then went to France as a research engineer. And he afterwards obtained a PhD in Bielefeld, which incidentally is quite close to where I was born. And now he's here as a postdoc researcher.
Good afternoon, everyone. So this is a work which I did in FIAS for the last 10 months. The research has been really very exciting and it's really very new, in the sense that this has a nice overlap for computer vision, where most of the times, like, you have this hard coding of rules in computer vision, whereas in this project it's not just about hard coding of the rules. When we see now, the rules actually autonomously emerge. So previously I was into the regular computer vision engineering part, so now I'm into the neuroscience of vision, and I find this really exciting now. So the project basically is it basically possible to autonomously learn eye movements as a function of efficient coding. So this is basically a collaborative work with a former postdoc here, who is now an assistant professor in France, and another group at Hong Kong by Professor Berchi. So let us say this is our visual system. So we have these two eyes. These two eyes have a field of view, and we have a scene over here. Now, depending on the convergence or the divergence of both of these eyes, we have partial or full overlapping images which falls on this eyes. And then we have this visual cortex which is on the backside of the hemisphere of the brain. So this data transmits over here, and this visual scene which is actually sensed transmits over here. And then there is lots of information flow that is happening back and forth. So just recently one of the groups at the MIT came out with a lower bound of what we actually get as a visual input every second. So that's around 10 MB per second. That is a raw visual input. That's the size of the visual input which we actually get. And having this kind of a data, even on a GPU processing machine, is quite hard to process. Now, how does the brain actually handle all these things? And by handling all these things, how are we able to learn specific eye movements depending on how the scene actually is and how the scene actually changes? That is the part of this research which we did here. So in the earlier parts of the 1960s, there were like lots of works about hypotheses and conjectures about how the brain actually handles this much of visual input, and how does from the volume it extracts the information and tries to process this information, and also sends so much of information back and forth among so many different areas. So we have this work from Barlow and Attenew, which sort of said that you have this volume of data that's actually coming out there, but it's not just the volume, but it is just the information that is there within this volume of data that is actually there. And the brain would rather apply some principles of information theory to extract the information per volume over there and try to store it and try to process it and try to make some cognition out of it. And sometime in the late 90s, you had a group from Brewer-Ohlhausen who actually hypothesized that the way this is actually done is through sparse coding. And then in another parallel work by Simoncelli and co., they said that you have these receptive fields which is on the back of the hemisphere of the brain. So let us say that this is a hemisphere of the brain and this has the visual cortex, and we have the receptive fields over there. And these receptive field profiles are sort of influenced by the natural scene statistics. So we had these kind of disparate amounts of works that are happening over there. So the very purpose of brain doing all these things is, one, it really wants to come out with an optimal representation for the signal that it actually senses without actually having any loss in ideal condition, or at least trying to minimize the loss. The second part is that if this is a theory, practically this is sort of realized in terms of neural circuits by doing a sparse coding stimulation of the receptive fields. And then that these receptive fields, which are there in the visual cortex, have a profile which is sort of influenced by natural scene statistics, by which the eyes and the brain are sort of exposed to the visual scenes.
Could you explain the term of sparse coding? What does it mean in general?
Okay, I'm getting into it. So this is the conventional efficient coding or the sparse coding. So we have the statistics of the scene, and this is sort of mapped into sensory representations. For example, let us say that this is the scene that we have over here, a picture of an airplane, and then we have a set of basis functions over here. So let us say that we pick one of these parts of this aircraft over here, and this part of the scene is approximated as a linear combination of these 5 basis functions. So the assumption is that these basis functions are sort of orthogonal, and as a linear combination we will be able to approximate this part of the image over here. So the analogy here is that this is a mathematical representation of what happens in the brain. So we have these receptive fields which are sort of surrogately represented by these basis functions over here, and when we are exposed to any kind of stimulus, this stimuli is reconstructed as an activation of a subset of the receptive fields that we have in the brain, and not everything. So the first thing that we really have to look is that if you look into this image over here, so this is sort of the aircraft, and this aircraft part is rather informative, and if you look into this part over here, like there's a sky, and this is just a repetitive pattern over here. So the thing is that we have an image and it has a lot of volume. Each of these volumes is sort of boils down to each of these pixels at the lowest level, but the information that is actually which is actually consistent in the image is not directly proportional to the pixels that are there. So per pixel information that we get is not actually very high, and that is how there is some regularity in the patterns that are there in the natural scenes. And then once we actually find out, we actually approximate these areas and then also update these basis functions. So this is how the receptive fields in the brain actually evolve, that we actually see some scenes and then we have the receptive fields which get activated, and these receptive fields change their profiles. So one of the main advantages of doing this is that it has a reduced metabolic cost. For example, we have a couple of millions of receptive fields over there, and then there is a scene. It's not the case that all of these receptive fields are activated, but only a subset of them is activated. So whenever we activate something, there is a consumption of power. So the goal is that we try to do our process and cognition by minimizing the usage of power in the brain. The second is that there is an increased amount of robustness in the system. For example, there are millions of objects and millions of scenes, probably infinite, what we can actually sense from our eyes. But the cognitive power that we have in our brain, which is sort of restricted by the number of receptive fields that we have, is rather finite. Now with this finite resources, we are able to recognize and classify infinite number of scenes and objects. So it's not the case that we have one specialized receptive field per object. For example, that let us say if we assume that we have like one or two receptive fields which are sort of specialized for face recognition, and in case of some damage to the brain, and if those receptive fields are gone, it's almost impossible for a person to do some face recognition or object recognition. But in normal cases, neurons actually die, they are sort of replaced, and in that way systems are actually built in a robust way that this ability to discern and recognize objects are not confined to just one single receptive field, but are distributed across many receptive fields. And the other part is that by identifying the redundancies in the whole scene, the system sort of says that, okay, these are the unique symbols that are there within the whole scene over there, and then it is not necessary to encode the entire scene, but just encode what is informative in the scene and then do replication overall. So this comes out with the additional benefit that you can just store the whole information in a reduced space, and this is sort of compactly represented. So in image processing and computer vision, they do something like run length coding, lossless compression, and a lot of other things, but this is quite similar to what happens in the brain. So once we have a scene like this, the conventional way the sparse coding is done is we have an image, and from the image, we keep changing the scenes, and with the change of scenes, the basis functions are actually learned and updated, and then in the end, we keep doing this process iteratively. And the regular way the sparse coding is done is that the system or the user has no control over what input it actually receives. It is just something that is actually thrown out from one data set, or what is actually decided by the user. So this is what the conventional state-of-the-art systems look like. But the point that we would really like to make is that the scenes which you actually saw were sort of just single images. But as far as we humans or mammals are concerned, we have a binocular vision system. So we have two eyes, and it's not just we sense one scene, we actually sense two scenes which have some kind of overlap. They already have some redundancy in them. Then these scenes are not like dramatically changing. They incrementally change, and they have a temporal effect. I mean, probably one example could be that the grad student would actually get into the decan's office filing for an application to get into a PhD program, and the next thing that the grad student would actually envision is his disputation and getting his degree. But in real life, it actually doesn't work that way. So there is a temporal change in the scene which actually incrementally changes. And there is also an amount of redundancy and overlap between these changes temporally also. And in addition, it's not the case that we have like static camera like a situation in our eyes. Our eyes actually move, they orient, they look, and scenes also change because of our eye movement. So they have some kind of an orienting behavior. The question which we really want to ask is that, is it possible to use the orienting behavior or the eye behavior to efficiently code the scene? So this we basically want to call it as the active efficient coding. So we have the statistics of the scene and we have the sensory representation. So this was the case in the conventional scenario, and now we would like to bring in the issue of eye movements, which also control what the system actually perceives. So it's not just done in a passive way. So this is sort of active and interactive. The whole system is reactive now. It's not just happening in a standalone situation now. So this is active efficient coding, and this is our contribution here. So we have the statistics of the scene, which rather drive the sensory representation. Now we also know that the same sensory representation drives the eye movements, and eye movements actually change the scene, because once they move, the scene changes, and since it changes, again the sensory representations are updated, and this process goes on infinitely. So here we should have had the efficient coding, but since we have the eye movements also factored into, we have the active efficient coding part, and here we do a reinforcement learning, wherein we have a sensory representation and we learn how to map the sensory representation to motor actions. So motor actions in the case is eye movements. So eyes basically have like a pan, a tilt, and a convergence or a divergence movements. So can we actually map this sensory representation into this convergence, divergence, pan, tilt movements? That is what we learn over here. And with that, the eyes again change the scene, update the beliefs, and from the beliefs, update our beliefs about how we should do motor actions. So the experiments were actually conducted on the iCub platform. So just to give you an example of how Vergence movement looks like. So we have one object which is actually moving on the depthwise plane, and we have these two eyes, and the eyes actually converge and diverge. The very purpose of doing all these things is that the system wants to see the same image of the finger on both these eyes to be identical. That's the very purpose of doing these eye movements. And if we look into how a smooth pursuit actually would be, that we have this object which has a frontoparallel motion, and the eyes actually move left and right, and maybe even top and bottom. And again the goal is that once you have an object here, and if it tries to move here and back and forth, the eyes move in this way or that way, just to make sure that it sees the same object temporally. Well, it should actually move up and down, but it's actually not shown there, but it actually moves up and down this way. So just to distinguish ourselves from the conventional robotic models, so most of the robots do actually have some kind of models of smooth pursuit or Vergence, but the thing is that these cameras in the robots needs to be calibrated. So this is some kind of a pre-processing that in advance needs to be done. Here we do not give any calibration parameters. Then the second part is that, as I said before, that this is not the conventional way of coding the scene, wherein we have a batch of images and from that we just learn our basis functions and then just keep doing it repetitively. But the system also has a control over what kind of scenes it can see and what it doesn't actually see. So this is the active efficient coding part. And then our goal is that by doing this, does it actually lead to efficient eye movements? And this is what we have seen through our research, that it actually leads to accurate Vergence and smooth pursuit eye movements. So this work is basically a continuation of the work that was basically done since 2007 from Bertschy's group, and also when Johan was in UCSD. And then there was a work which was not actually put on the robotic platform, but it was done on regular images. It was rather simple, and this work sort of inherits all of those things and sort of subsumes the works on smooth pursuit and also on Vergence eye movements before, done in Hong Kong and also by my predecessors at FIES. So just to explain you a bit more about how our model actually looks like. So we have this robot, and we have two eyes of the robot, and from that we have the scenes which are actually sensed at given timestamp t and just the preceding timestamp, both from the left eyes as well as the right eyes. So this is approximately how the scenes would actually look like within the simulator environment. So we have this left and right eye scenes at time t and t minus 1, and this we actually decompose into coarse and fine scales. So we operate not just on one scale but at two scales. So one is that if you actually look at these gratings here, so we just put a square in the center. So this is approximately where the system actually fixates when it's at the beginning of the learning process. So we have these gratings which are rather fine, and you have these gratings here which are slightly bigger. So this is basically done for the sake of convenience, in the sense that this is sensitive to smaller velocities and this is sort of sensitive to larger velocities, and the system becomes more robust when the image actually moves back and forth at different depths. So this is just a zoomed up version of that previous center of the attention fixation point, and from here this is how we extract the features. So we have spatial information, and we also have temporal information here. So we end up getting this spatio-temporal patch field, wherein we sort of concatenate the corresponding spatial and temporally allocated bins into one single field over here. So this is not just the case, this is just an example wherein we show that we do it like this for these patches, but it's ditto done for all the other patches there. So the second one over here is concatenated with the second here, and also the second and second, and so on and so forth. So this is the representative feature vector over here. We don't actually operate it on the color version of the image, but rather we operate it on the z-scored version of this image. So we have a unit norm and zero mean for all of these things, and sort this is whitened. So this is done in order to remove the correlations between the pixels that are there already. So this could actually lead, if we don't do it, it would actually lead to spurious results, and it would not help us do some orthogonalization. And the next part is that once this is done, once we have these patch fields, we go ahead and encode these patches using a set of dictionaries. So we have these basis dictionaries which are randomly initialized, and we have these patches, and in the end we want to actually encode these patches using this set of dictionaries that we already have. So we have these 4 fielded patches over here, and again our dictionary elements also have a 4 fielded there, just in order to correspond to these 4 fields here. So we basically use the matching pursuit algorithm to reconstruct the signal using this basis set of basis functions, and in the end we end up getting a reward signal, and the reward signal here is the reconstruction error. So in case the dictionaries are perfect, it would be able to reconstruct the signal with almost no error, and in case the dictionaries are not very good or for any other reason, then the reconstruction error would be slightly greater than 0. And the second part is we have this data which is encoded. So the encoding of the data is basically the coefficients of the sparse basis functions which we use to reconstruct the spatio-temporal patch field. So these are the coefficients which are basically used as a multiplying factor for the basis functions that were selected to reconstruct these patches. And the next part is, once this is done, we actually update the basis functions. So these basis functions were actually initialized randomly, and now we use a gradient descent to update the basis functions. Maybe I can go back, so maybe you can focus your attention over here and see the basis functions being updated using a gradient descent rule. And since we are using a gradient descent rule over there, the goal basically is to minimize the reconstruction error again. With this, we pass this reward signal and also the encoding of the data to a reinforcement learning mechanism which actually maps out the motor commands so that the eyes move and sense the new scene at the next timestamp. So this is basically how a reinforcement learning actor-critic network would look like. So we have one network which basically learns to map the representation coefficients to one of the motor actions. And then we have a critic network which basically accepts the reward signal and promotes those actions which increase the coding efficiency. So the reward signal basically here is a reconstruction error. Now the thing is that as and when the reconstruction error decreases, or it would promote only those actions which would lead to reduction in reconstruction error, which means to say the system would like to see more redundancy between timestamps and also between left and right eyes. So for our robot, we basically have 3 degrees of freedom for our eyes. We have a pan action, then we have a tilt action, and then we have a vergence, a convergence or a divergence eye movements over here. So we basically have 3 sets of actor-critic networks which learns to map pan, tilt and vergence actions independently. And then This again updates the eye movements, and then this process goes on in principle indefinitely, but we stop it at something like 1,000,000 trials. So this is how the simulator environment looks like when we start the training process. So we have this iCub robot, which is, this is basically the simulator, and you can actually see the eyes moving, and this is basically the anaglyph. So this is like the blue images are the ones which the right eye senses, and the red images are the ones which actually the left eye senses. And if the left and right eye actually sends the same kind of images, and when these two images are overlapped, we would not see any kind of blue or green tessellations, but one would rather see a grayscale image. So the reason why we actually end up seeing this kind of tessellations is that the left and right eye doesn't really have any kind of coordination and doesn't really see the same kind of scene over here. So to explain a bit more about how we conducted our experiments, we have a set of these planar objects which move in a specific velocity at a specific depth, and then we keep changing these objects and also keep changing the depths after some specific number of trials. Approximately after every 10 trials we change the depth and also the pan tilt velocity of the objects. And this is how the basis functions actually look like in the beginning. So this is like they are sort of randomly initialized to start with, and as and when the training trials progress, one can observe that the reconstruction error starts going down, and as and when the reconstruction error keeps going down and saturates, you don't see any drastic changes after the basis functions have been converged over here. Now that we see that these basis functions sort of converged, and we also have a good reconstruction error, does it make any difference for our eye movements?
Just one question about your convergence. So you started from some difference of 0.3 and like it's decreasing only 3 times. So maybe even without any convergence and without any learning, it's already quite good.
No, it's not the case. Like you have this. You can basically look over here. So here you have some kind of a noisy initialization over here. So then the reconstruction error which you actually see here is basically smoothed, is a moving average. So you don't actually plot the actual reconstruction error over there, it's basically a moving average. Since you have a moving average and then it's also sampled at some discrete intervals, you don't actually see the basic spikes. But if you actually put the real data and don't actually sample it and don't put a moving average, one would actually see that you would have like reconstruction error of close to 0.9 and 0.85. So this is just to make sure that the graph looks clean, and it conveys the point that as and when the reconstruction error reduces, you have a convergence in these basis functions.
So this is like average error over your cells, but there is also like sigma,
yeah,
which you don't have.
Yeah, because it's close to something like 1 million data points over there. So it's quite hard for the viewers to discern it.
But you could also plot sigma, which is the deviation from average, and you could see that your sigma converges also.
So there's a plot in the next slides. So in the end, this is how the simulations actually look like. So now we don't end up seeing any kind of blue or green tessellations over there, but we clearly see that we really have one nice grayscale image, but then there are some shifts here and there. That's because the object actually changed its depth, but otherwise it really started moving its left and right eyes in a nice coordination, and then end up seeing only one view and not 2 different views. Now to quantize how the eye movements performance actually had. So we actually have a pan and a tilt and a vergence actions, and now you can see that as and when the training trials progressed, with the increase in the coding efficiency, you could see that the error over the pan action and the tilt action and also the vergence action really reduced over a period of time and it starts saturating. So this really shows that using coding efficiency as an objective would help us lead to accurate pan, tilt and vergence eye movements. So again, to give some highlights, we did not ask the system to explicitly learn any eye movements, but what we actually asked the system to learn was to represent the scene in such a way that it is compact, optimal and efficient. The goal was not basically to learn either vergence or smooth pursuit eye movements, but in the end the system discovers that it can actually achieve the objective of coding efficiency by doing the appropriate pan, tilt and vergence actions. So in our case, the smooth pursuit actually maps to appropriate pan and tilt actions, and of course the vergence eye movements is basically either converging or diverging eye movements. So by appropriately doing these actions, the system is able to encode the scene far more efficiently. And one has to bear it in mind that this was done on a robot and it was not given the camera calibration parameters. So the system is rather self-calibrating. Now if we actually look into the basis functions that we have, so this is how approximately look like. So this is one of the basis functions that we obtained. And now they sort of resemble the GABA filters. Now if we have a basis functions and if they start resembling,
What is a GABA filter?
okay, I have the formula, see I can show you there. So does it really have any biological significance at all? So the point is that it's quite well known in neuroscience that the receptive fields that we have profiles which is quite similar to GABA filters. So this was one of the first papers which actually mentioned that. And a GABA filter is basically can be described by this function over here. So it has a wavelength, it has an orientation, it has a standard deviation, a set of centers. And what we basically did was that we have these basis functions and we try to approximate these basis functions by using an optimization routine and try to discover these parameters. So this is how the fitted GABA filters as corresponding to the original basis functions that we had actually look like. And the fitting procedure was that we had these 4 of these subfields, and from 4 of these subfields we keep this set of parameters as a constant, but we change this phi parameter. So this is the phase difference in the GABA filters. And the reason that we actually did this was that with this kind of a formulation we can actually quantize the disparity preferences and also the velocity preferences of the basis functions.
Do you mean by quantize?
I mean we can actually come out with a quantitative representation of quantification of disparity in velocity preferences. So this was how the disparity preference actually looked like. So now there is a reason why we actually use this. So this formula is valid only if we do the fitting in that way. And now if we can actually look, majority of these basis functions have a disparity preference of 0, which means to say the system actually likes to see when there is 0 disparity. So 0 disparity means that the left and the right eye actually end up seeing the same kind of a scene, and that's possible only when the actor critic network knows how to converge or diverge appropriately depending on the depth. It's able to sense the depth based on the reconstruction error. Now again, if we look into the velocity preferences of these basis functions, again you can see that there is a huge peak on 0. In our simulations we actually had objects moving at something like 15 to 25 meters per second, but the basis functions here, almost 60% of them are tuned to 0 velocity, which means to say that despite the shift in the objects in a temporal scale, the eyes are able to move appropriately and track the object, and since it's tracking the object appropriately, the basis functions would like to see no differences between images at time t and t minus 1. And when we actually plotted the preferred velocity versus the preferred disparity, one can see that there is a big blob here at 0. It wants, the system would like to see 0 disparity also and 0 velocity, but there is a high amount of variance in disparity preferences, but there is a low variance in velocity preference. So the system was not biased to come out with a plot like this, but this has some grounding in the neuroscience that most monkey V1 cells have a disparity and a velocity preference, a joint preference of a basis function in this way. However, we obtain this result without having to bias the system in any way. To summarize this talk, so we basically introduced the concept of active efficient coding, wherein the system is not just provided with a batch of images, but the system also has an eye, and the eye is able to reorient itself and sense the images. Then this is, to the best of our knowledge, is the first time wherein we are able to come out with a set of basis functions which can jointly represent both velocity and disparity. They have been works sometime in 2009 from a group in Colombia, but the model is quite theoretical and they haven't really been able to learn it from in kind of an autonomous kind of a setting, because all the rules were rather hard-coded, and this also has a possibility to work in a real robot. Then our system is self-calibrating. So this is something which is a message for the robotic community, that the system is rather robust. There is no special module that we wrote to learn Vergence or smooth pursuit behavior, but the system was able to learn all of these things by itself just by looking into solving the problem of actively encoding the scene in an efficient way. And we are trying to extend this model for strabismus and amblyopia. So this is some kind of eye disorders, and part of the work has already been done by our collaborators in Hong Kong. So all the settings and experiments that we did was on the iCub robot, and Alex has developed a new simulator wherein all of these things could actually be ported and learnt more realistic, in the sense of being more biological and more nature realistic. Because in the iCub robot, there is a constraint of the hardware. It makes lots of assumptions that the vergence of the left eye is exactly the same as the vergence of the right eye. Then there is a velocity that is sort of restricted by the motors that are there in the eyes. So Alex has developed this simulator, which he calls as OpenSim, and with this it has an eyes and it has muzzles over there, and the question is that whether controlling these muzzles and using these muzzle models for actively encoding the scene and doing exactly the same way, how would it actually change our results, and would it rather help us analyze and understand the data that is there in the literature already much better than what we have. So this is what Alex would investigate over the next 6 months. So this is not my simulator, it's Alex's simulator. So you can ask him over there for more details. So thanks a lot for the funding agencies. Thanks for Professor Birchie for hosting me in Hong Kong for 2 weeks. Thanks Johan for hiring me. And thanks all of you for being patient enough in listening to the talk. I still hope you have some pizzas left.
I think so.
Okay. I'll be happy to take some questions now.
Okay. Do you have questions? Yeah?
So it looks like a finished work. What are you planning to do next?
Well, there is. It's not completely finished. So we have. You could actually see that we had these objects and it were moving in front of parallel plane, but in real life the objects don't just move on a frontoparallel plane. You have like a 3D motion which actually moves zigzag or randomly. So that is the next part of the work which we are doing, which we have done rather, and we are writing it up. And then there are really lots and lots of exciting things over here, like if you close one eye and if you have the other eye, so it's a problem of accommodation. It's a problem how does the basis functions look like when there are some visual disorders, ophthalmological disorders like strabismus, and these things can actually be much better analyzed in Alexis simulator. You have these 6 muscles which actually control the eyeballs, and in case one of these muscles are actually dysfunctioning, how would the patient actually see those images? So it's like it's a vast area of research, and you can just keep spending the next 10 years doing this.
Okay, so you can kind of have 30 muscles, you have kind of 6 multiplied by 5 combinations.
Yeah.
How you can switch on
Yeah.
on and off.
Yeah. And also there's a lot of work which we haven't used here. So it's like we used an off-the-shelf sparse coding mechanism, we used an off-the-shelf reinforcement learning mechanism, and also the simulator. So that was also off-the-shelf. So now Alex has a simulator. The question is that one can also invest a lot of time in doing some biologically inspired sparse coding, biologically inspired reinforcement learning mechanisms, and trying to put it on Alexis simulator and see how it actually looks.
I'm confused about one thing. Maybe that's something that I'm missing. So, in order to compute this reconstruction error, you need to have both the representation via your GABA functions and the stimulus itself, right? So you need a difference between the two. So how is? But then the external world sort of has to be represented as well inside the device, the robot, or the brain. I mean, the robot you can, I guess, do this, cook it up. So how do you think of this representation?
Okay.
How do you think of it in terms of the robot, and how do you think of it in terms of the visual system, like a primate? Like, how does the primate compute the reconstruction error?
Well, I actually cannot say much about it because I'm not an expert in that field. But what I can actually say from the robotics point of view or the computer vision point of view is that these basis functions, each of these point in the basis function, let us say they are like sampled from some uniform distribution with 0 and 1, and then the goal basically is to come out with some kind of a distribution wherein it's not completely random and ad hoc, but it has some kind of estimators which have some kind of a nice standard of errors. Let us say that you have this estimator with a mean and a specific variance, and the variance of that variance and the mean do not actually change a lot. And this is something which is already being done in computer vision as such. So we have these stacks of images that are there, and from them you learn those basis functions. But in this case over here, the most important advancement here is that what we already had was that these two images, which was actually presented in a batch mode, need not have any sort of correlation overlap between them. And in our case, we have these cameras, and we are able to reorient the cameras, and from those cameras, it's already sort of driven or biased by the basis functions that we have. So we have a basis function, it's sort of biased, reorients, then it updates the basis functions again. So this is sort of like biased development, and it's not like a batch kind of a development.
Yeah, but I mean, I was thinking, I think Noah had the same question, because if you want to calculate the reconstruction error, you need the real image and you need the representation. But if you say this is a model of a brain, then you only have the representation, right? Because how should the real image come in? Okay, so well, at the point, this is the best that we can get in this domain. So the thing is that since we already have a robotic model over here, it's not just in this assumption, there's lots of assumptions that are going on here. We really don't know whether we have this kind of an actor-critic mechanism in the brain. I mean, this is a conjecture again. So all of these things are conjectures. They really have some kind of 80 to 90% overlap of how things are done, but
we are not really sure whether this is algorithmically implemented in the brain exactly in this way.
For the robot, you are assuming that the robot has access, direct access to the
Scene, yeah, it sees the scene.
Yeah, but does seeing mean the processed image after representation, or the real image as well?
Well, it actually sees the real image and then processes the real image.
Okay, so it has two
Yeah.
points.
So it has a real image, and from the real image it processes, and then again a lot of transformations happen over there.
Then it compares the real
Yeah.
image that it received with the
Yeah.
process.
Okay.
I have one more question about it. So, in your simulation, it looked like you have some patch of an image which you're moving, and behind you have another scene, right? Which
Patch of an image, I mean,
so in your movies, you showed like a picture
okay.
moving in front of your robot, but you also have some background scene.
Yes. Yeah.
So what I'm not completely getting, if you get a good simulation in the middle of the scene or in that patch, then you actually get worse in the surrounding, right? So your
Okay.
error, you computed well all the scene or only the
No. So this is the whole operation is basically done just at the center. Only on the center. So this is just done only on the center, because if you end up taking the whole scene, if you just end up taking the whole scene, then it would be the case. I mean, there are lots of problems over there. Like, for example, let us say if this object is not there and we just take the whole scene, and let us say we converge or diverge it just a little bit, since there is so much of redundancy, the reconstruction error would actually drop down. And let us say that if the robot actually just starts looking at the floor and not looking at the background of the scene, if it looks at the floor, you have these tiles, and the tiles look quite redundant, and it doesn't change over a period of time, then the robot would actually think that, okay, it has learned something. So the point is that it has to look straight, and then it's made sure that it's not just looking just at the background, but it just looks at the very small part of the scene and tries to reconstruct it. It's not about the whole scene.
Okay, well, that would also mean that it has to look straight, and if some object comes from the side, then its beginning doesn't work. So it has to come into the center and then begin moving so that you learn this.
It's, well, to start with, when we actually learn the training program, this is how it actually happens. But after the system has actually learned, it's quite robust. So there are some more experiments which I haven't actually put over here, that even if some object comes, or it's rotated, or it's distorted, or pushed back and forth dynamically, the system is still able to adapt to it. So there were some experiments which Celine had already done. So there are some videos on the FIAS site about that.
Okay, I see no more questions. So let's give Rika a hand.
Thank you.